This is a description of a project I'm calling Idaho Avionics. The DIY electronics market is growing, has been for a while. These are the Arduino and Raspberry Pi hackers. And then in another part of the world, the experimental aircraft market is growing. These are people who build and modify their own airplanes. Uh, the intersection between these two markets is hackable avionics. One product can add something to both of these markets. Um, so what I'm proposing is an Arduino compatible circuit board with a unique set of um, peripherals that lend themselves to avionics. And what I'm offering to the other side is an electronic flight instrument with more capabilities than any other that's currently available, at least for the price. So the goal is to create an electronic flight instrument. I'm calling it Product A for now because I don't have a better name. This is to be reliable, meaning that it has battery backup and it can talk to other such devices to detect faults. It's hackable, meaning that it runs Arduino or something like that, and is not closed. You, right out of the box, can program it yourself to do something different than what it's packaged with. It's extendable, so we'll use common standards, CAN bus, Wi-Fi, Bluetooth, things like that. And it's affordable. So similar products that exist today are range from $1,500 US to $3,500 US. Very often they come in different types. So you have a product that comes in 3 different flavors to do 3 different things. I'm proposing a single product at a reasonable price that can do any of those roles that current products can do. Um, and then it needs to look good because we appeal to a wider audience and we feel better about what we make when the product looks good. So I'm calling this product A, don't have a better name for it, and that's just a conceptual drawing there. About myself, I'm a private pilot and an airplane owner. I'm a very low time private pilot, meaning I'm very novice, still learning a lot. I've owned 2 airplanes. The one on the left was my first aircraft, a Cessna 150. That's a certified aircraft, so you can't make modifications like build your own avionics. And then the one on the right is the current aircraft I own. It's called a Murphy Moose, and it is experimental category, so I am allowed to do things like build my own avionics. I'm also a software developer, and I live in Idaho in the United States. So these are what flight instruments are. I'm going to be very broad, general. Uh, 3 of these instruments are driven by barometric pressure. Those are the airspeed indicator, the altimeter, and the vertical speed indicator. Then the attitude indicator, heading indicator, and turn coordinator are driven by gyroscopes. Each of those in a mechanical instrument have their own gyroscopes inside that do different things. Um, and so there are these 2 general categories of gyroscopic and barometric. Then on the right, we have a magnetic compass. Um, the heading indicator in the bottom middle is gyroscopically driven. It usually does not have a magnetic compass built in, so you have to correct the drift every now and then. Okay, then according to the FAA, the instruments on this screen that are required to fly an airplane are the airspeed indicator, the altimeter, and the magnetic compass. The rest are optional for visual flight rules flying. A little bit about electronic flight instruments. A primary flight display, as you see in the middle, is a portal to view the flight, what is the equivalent of the mechanical flight instruments. And then a multifunction display on the right over here is a display that can display anything you want. It can show a PFD type view, or you can usually do a lot of like navigation moving maps type of things on that display. These are usually just displays. They are not the sensors and the gyroscopes themselves. Normally, these are just the displays. And and then there's this thing called an ADAHRS or AHRS, a little box that's connected to these displays, and that's where sensors are, sensory input is synthesized and then forwarded onto the displays. On the left here is what I call a round mechanical upgrade. This is an instrument that's made to fit in the panel of an aircraft where one of these older mechanical instruments was. And so it's an upgrade usually because a mechanical instrument can only perform one or two functions, but an electronic instrument can normally do a lot more than one or two functions. So it acts as a replacement for mechanical instrument and also as a backup for other mechanical instruments. Okay, so flight instrument sensor collection is often referred to as ADAHRS. I'll use that term ADAHRS later. Okay, then there are instruments that are not quote unquote flight instruments. These are engine monitoring, navigation, communication, and then others miscellaneous. Navigation is a moving map or course deviation indicator. Moving map is more of the electronic style of that. A course deviation indicator is more of the mechanical style. And most of what's in here I won't go into with product A, at least not right away. So a description of product A is a round electronic flight instrument. It functions just like any flight instrument. When multiple product A are installed, they can intercommunicate for fault detection. So if the inertial measurement unit in one fails or starts doing something funny, then it would be comparing its results to another, and so the two instruments would uh, signal that, hey, one of us is wrong, we don't know who. Product A is controlled with two concentric knobs and a push button. So that's down here at the bottom right of the conceptual drawing. Two concentric knobs, one on the outside, one on the inside, and then the inside concentric knob is, you can press it as a momentary push button. Product A also emits audio tones for stall warnings and maybe other kinds of warnings. Those audio tones are forwarded to the intercom. The software is updated and configured via Wi-Fi, and because all the configuration is done through a web browser, the physical interface that you're flying with can be as simple as just that two concentric knobs and a push button. External connections on this device. We need DC power. That's usually the usual 12 to 14 volts. We'll need a pitot-static, so a pitot tube and a static tube. These are sources of barometric pressure. Um, and static pressure gives us altitude and vertical speed indication. And then the pitot tube combined with the static pressure can give us airspeed. A third pressure tube is angle of attack. That would be kind of an optional add-on here. It's easy to add a third barometer, so I put it on the product description. Thermocouple is also kind of optional. A thermocouple allows you to measure outside air temperature, which is useful for several things, but it's not a required instrument. Of course, the audio output for stall warning, and then Bluetooth, Wi-Fi, CAN bus can be used to interface with other instruments and an iPad or a phone, and then of course a computer for configuration. So internally, the product is divided into two modules. The first module is the one that you think of when you see it. That's the user interface. That's a round LCD, 3 inches in diameter. It's the knobs that I described, and it's the audio tones that come over the headset. And on the right is the ADAHRS module. And this is where we collect 8-hour signals. So it's airspeed, altitude, and vertical speed with the barometers, and then it's attitude, heading, and turn coordination uh, with the inertial measurement unit. And we use a 9 degree of freedom IMU, not a 6 degree, so that we can continuously correct for drift in the yaw axis. And that way we don't need to correct for drift manually. And then, as I mentioned, the thermocouple decoder is for outside air temperature. And again, not a required feature, but a nice to have and not difficult to add. So the modules in detail. For now, I'm going to try an ESP32 with a TFT driver for the user interface. There's a lot of software to write, and there are alternatives that I could fall back on. ESP32 is not something I'm particularly tied to yet. There are a few STM32 systems on chip that include graphics or display accelerators, and then of course we could just go to a microprocessor like an ARM A series and um, run a full operating system like Linux. So lots of software to write, and the user interface receives the information it's to display via I2C. So over to the 8 hours module, which is on the same printed circuit board. We'll use I'm going to try the RP2040, which is what's used in the Raspberry Pi Pico. Very capable microcontroller and very cheap. So I want to try that first. Most of the input sensors, most barometers and thermocouples and IMUs are available with I2C output. And so I will try to stick with I2C for the input to the 8 hours and the output from the 8 hours to the user interface module. And there's just more of that same diagram, a conceptual diagram. On the right here is a side view. So you can see that there's some relief in the medium gray, and that's where the circular hole and the circular um, instrument would fit together. And something I've thought would be nice is that knob is positioned at the bottom right on the left diagram, but there's no reason that it couldn't be positioned on the bottom left. In fact, it should be trivial with software to allow positioning in any of the four orientations. Okay, that's all I got for now. I'll try to update this as it changes.